All right, so I wanted to do an example of phasor analysis and just how to, do some things like we've been doing in the homework. So let's say I've got um, two sinusoids. One is 100 cosine 2 pi 1000 t plus 86 degrees, let's say. And let's say the other one is 10 sine 2 pi 1000 t plus 88 degrees. Okay? Now, let's say the question is that you want to find what is x of t plus y of t. And let's say I want to know both what is the complete waveform and what's the phasor. Okay? So to do that, I got to go in a couple of steps. One, the first step is write x of t and y of t in phasor notation. Okay. Now to do that, I want to make a point real quick. So let's say in general, just remember that e to the j theta equals cosine of theta plus j sine of theta. And we say what that means is if I have this, and maybe I'll add an amplitude to that. Okay. That says that I've got a vector whose length here is a and whose angle is theta. So the real part here is a cosine theta, and whose imaginary part here is a sine theta, right? All right, so it's just a way of keeping track of all of that. All right, so I can look at x of t and y of t that way. So let's look at x of t. Okay, x of t was 100 cosine 2 pi 1000 t plus 86 degrees. Okay, what I can do is I can say that theta is equal to 2 pi 1000 t plus 86 degrees. Okay, that means I can rewrite this guy as 100 cosine of theta. Now, important thing so how do I relate this to phasors? Well, if I go back to my original Euler's identity above, the real part of a e to the j theta is a cosine theta. All right, see the relationship between those two. The imaginary part I define as a e to the j theta. The imaginary part of that is a sine of theta. Okay? So what I can see right here is that using this relationship on this guy, I can see that this must be the real part of 100 e to the j theta, which, given the way that I have defined theta here, is the real part of 100 e to the j times, and I put in the whole angle, 2 pi 1000 t plus 86 degrees, like that. Okay, it's the real part of that whole thing. And then I can say, well, this guy looks like to me e to the a plus b, where this term is a and this term is b. So I can rewrite this as the real part of 100 e to the j 86 degrees times e to the j 2 pi 1000 t, like that. This thing right here is what we call the phasor. Okay? Knowing the phasor and knowing the frequency, we can always go back to whatever the original waveform was. So let's do that. So here I'm going to say my phasor x underscore is 100 e to the j 86 degrees. So I've got that phasor. Now let's do it for y. So y of t is a little bit more complicated. Y of t is a sine wave. So I've got 10 sine 2 pi 1000 t plus 88 degrees. All right, now I got to be careful here. So sine, I see, is the imaginary part of a e to the j theta. So that gets a little bit tricky. All right. So how do I deal with sine? Well, because we define the phasors as basically this, what we call the complex amplitude, this 100 e to the j 86 times the time domain part, right? I need to convert this to some equivalent cosine waveform. So here's the way I look at this. E to the j theta is cosine theta plus j sine theta. That you should remember, all right? That's a key relationship that you should remember. If I were to multiply that guy by minus j, e to the minus j, so minus j times e to the j theta, that becomes minus j cosine theta. Then I have a minus j times a plus j times the sine of theta. Now, so j times j is minus 1. Then I have another minus 1, so that makes it positive. So this becomes minus j cosine theta plus sine theta, like that. So typically what I do is I say, well, if I have a sine wave, I define my phasor as real part of minus j a e to the j theta. All right. This is how I define a sine wave, because if I write this out, this guy is going to be a sine theta. All right. What it's saying is, what am I doing when I multiply by minus j? I can think of this two ways, right? I can do it the way I just did it. The other way I can say is, if I have a complex number minus j times e to the j theta, I could do this. So here, when I did this, this was in rectangular coordinates, right? Well, here I can also do it in polar coordinates, right? And I can remember that what I'm doing is I'm multiplying two vectors, so I can essentially look at the two things in polar coordinates, and I can say, well, you know, with this minus j right here, this looks like a vector that has a length of 1, and minus j has an angle of negative 90 degrees, so I can write him also like this. So that says that my answer here is essentially e to the j theta minus 90 degrees, like that. All right. Essentially, what that means is when I multiply by minus j, it subtracts 90 degrees from the angle of theta, which essentially turns sine into cosine, if you look at the trig identities, right? So essentially, if I have a sine wave, I take the real part of minus j a e to the j theta, and I get from that a sine theta. Okay, so let me take a look at this. How do I approach this now? So the original problem was y of t equals 10 sine 2 pi 1000 t plus 88 degrees. All right, and I called this theta. So I'm going to write this guy as 10 sine of theta. Now, that has to be the real part of minus j times 10 times e to the j theta. Okay, like that. And so, again, just I could write that out as a check, right, to see that that would be true, right, if I wanted to, right? Maybe I will real quick. So I have minus j 10 times cosine theta plus j sine theta, right, like that. If I multiply through by that minus j, I get this, plus 10 sine theta, like that, and I'll end up with 10 sine theta, which is what I started with, okay? So that's good. The question is, what does this thing tell me? So I need to look at this minus j 10 e to the j theta real quick, right? Remembering that theta is e to the j 2 pi 1000 t plus 88 degrees. So that becomes minus j 10 e to the j 88 times e to the j 2 pi 1000 t. Okay? This part here now, this is my phasor. Okay, so my phasor y hat is minus j times 10 times e to the j 88. So if I write that out, again, remember this guy here is e to the negative j 90 degrees, right? Because he's a vector that's pointing straight down with a length of 1, right? So that's a negative 90 degree angle times 10 times e to the j 88. So what I do, I have two complex numbers multiplied, so I multiply their magnitudes and I add their angles. So I get 10 times e to the j negative 90 plus 88, or 10 e to the j negative 2 degrees, like that. So that says that my y of t is the real part of my y phasor e to the j omega t. So in other words, notice what I did. It's the same expression as before. What I've said is that this y phasor here, oops, not that, right? I've said that this phasor right here, I plugged it in there. I've gotten rid of that minus j. I brought that 90 degree phase angle in there, 90 degree phase angle shift, right? And so I can write this as real part of 10 e to the j negative 2 degrees times e to the j omega t, which if I expand that out, it's just 10 cosine omega t minus 2 degrees, like that. Okay? So if I want to figure out how to combine my waveforms here, if I want x of t plus y of t, well, it's fair to say that that guy's got to be the same as the real part of x phasor e to the j omega t plus real part y phasor e to the j omega t, like that. So I say, all right, that's the same as x phasor e to the j omega t time plus y phasor e to the j omega t. So x phasor plus y phasor times e to the j omega t, like that. Okay, so now I need to figure out what the heck is x phasor plus y phasor. So x phasor plus y phasor. Well, that was, if I go back up, e to the j 86. Oops, 86. Like that. Let's see. E to the j 86 plus 10 e to the negative j 2 degrees. Now there's no easy way to add stuff in the polar form like this. So what I have to do, I really have no choice but to expand this guy out into rectangular coordinates. So I say 10 cosine 86 degrees plus j 100 sine 86 degrees plus 10 cosine minus 2 degrees plus j 10 sine minus 2 degrees, like that. Right? So then I have to basically add those up real quick. Right? So how do I do that? So essentially, I go in here and I say 100 times cosine 86 degrees. So this is 6.98. All right. Then I have 100 times the sine of 86 degrees. That basically gives me plus j times 99.76. Then I have plus 10 cosine of minus 2, so 10 times cosine of minus 2 degrees is 9.99, and then I have 10 times the sine of minus 2 degrees is minus j times 0.349. So I add those up. So I have 6.98 plus 9.99. I get 16.97 for my real part. So in other words, I'm adding this and this. And now I have to add the imaginary part, so I add this and this. So I have 99.76 minus 0.349. That basically gives us 99.41, like that. Okay? Now, to get this back to my final answer, we're going to need to get this guy into polar form to get an equivalent phasor. Alright, so let's see. How do I do that? Well, to get this into polar form, I got to say, what's the magnitude? So x hat plus y phasor, get the magnitude of that. So the magnitude would be square root of 16.97 squared plus 99.41 squared, square root of 16.97 squared plus 99.41 squared. So basically 100, a little bit bigger than that, 100.85. And the angle, so angle x plus angle y is arctan of the imaginary part, 99.41, divided by the real part, 16.97. So that becomes 99.41 divided by 16.97. So that becomes 80.31 degrees. So essentially what you're saying is x hat plus y phasor is 100.85 e to the j 80.31 degrees. So the answer is the real part of x hat plus y hat e to the j omega t, which would be 100.85 cosine of 2 pi 1000t, right, plus 80.31 degrees. Okay, that would be our final answer. Right. Now, this gets a lot easier if what you can do is you just recognize ultimately that the phasors here, that when I see this guy, I can quickly represent that for a cosine, I just get the amplitude times e to the j 86 degrees. If I see that's the phasor, that's pretty quick. For this guy, what I have to remember is the phasor is minus j times 100 e to the j 88 degrees. And I got to be careful. Sorry, I said 100, but it should be 10 for this one. All right, it should be 10. This guy has a different amplitude. And it should be 88 degrees. And what that means is that it's 10 e to the j 88 minus 90, like that. In other words, I subtract. So more generally, if I have x of t equal to a cosine omega t plus phi, my corresponding phasor is a e to the j phi. If I have x of t equal to a sine omega t plus phi, then the corresponding phasor is a e to the j phi minus 90 degrees, like that. So those two relationships are really the two outcomes. So if I see that, I can pretty quickly answer a question like the one that's posed here. Hopefully that helps to understand a little bit. Critical things for you guys to really remember are things like, all right, Euler's identity, remembering these relationships here, all right, remembering things like, once I'm down here and I'm adding phasors, how do I do that? Well, that's best done with everything in rectangular form, right? Once I want to get to my final phasor, I want to go back to polar form. So just remembering those sorts of relationships is particularly helpful. All right? All right, that's it.